So coming to machine learning is like a machine is learning, right? So what machine is learning? So you basically have data set. You go to the history. You want to, let us say, you want to do weather forecast. Okay, you want to do weather forecast, or let's say you wanted to do rain forecast. You wanted to do rain forecast. Um, what should I do? To do a rain forecast, I need to have all my past data for every day, how much rain has happened, right? And I also need to have information about which month it is, because there are sometimes it is rainy season, there are sometimes it is summer season, right? So we also need to have visibility. What is the visibility? How, right? What is the visibility? What is the temperature? What is the likely temperature that will happen tomorrow? All the sorts of information is required to not just that. I mean, you also have to know how much cloud has condensed over the sky. All those things are required. I'm just trying to give you an example of somebody out of you has told, right? You wanted to do weather forecast. So all this information are required. Now, taking all this information, we also took the history data, like in the previous days, how much rain has happened. So we know in the history that how much rain has happened based on some of the attributes, some of the features, some of the properties, some of the facts. All we need the machine to learn is learn from the past data how things happened. Okay, and you just now, given today's data, you tell me how much it will rain today, or given current data, you tell me how much it will rain tomorrow, right? So here what will happen is the machine will learn about the data iteratively. It will learn about the data iteratively, and it will first, okay, so what it will do is, first it will, don't worry about what kind of model I'll fit. Just think that a model is learning. A model is learning for last 7 days. Let's say for last 7 days, I have given some data to it, and I know that how much rain has happened in last 7 days. So a machine will learn on that data, and it will predict. Okay, uh, last 7 days, this much of rain has happened. But at the first attempt, it will make a lot of error. Okay, at the first attempt, let's say it makes 70% error. Then it learns from it. It takes a feedback from it. Okay, I have not learned it nicely. It goes for a next iteration. It tries to fit better. Next iteration, it may give you 60% error. It goes again and again and again. So on that, in an iterative manner, and it will try to learn more and more about the data. So, and maybe ultimately at the end of your iterations, it will end up with fitting the data with just 5% error. Okay, and that is the model that will evolve. Okay, that is the machine learning model that we generally do. So it's an iterative process. So to be formally defining, machine learning is a iterative process. Okay, machine learning is an iterative process where is a system, okay, a computer learns from the data and acquire the knowledge present inside the data. Okay, so you don't need to remember something here, but just understand. Okay, uh, what that machine learning is nothing. You just iterate through the past data and try to learn and be ready for predicting something. Okay, that is all about machine learning. So when we say, let us say you have been given some input data. So over here, I have some input data, and I want to run a machine learning model. So generally, what should be your strategy? You should not learn on the whole set of data. So let's say I have given you, let me take an example of, let's say I gave you some data set of identifying between an apple and an orange. Okay, I gave you some data set of identifying between apple and orange. Let's use a some sketch. Yeah. So let's say all I need to know is I need to. So let's say this is apple. I don't know this is apple or not. Okay. There's apple and there's orange. Okay. So yeah, apple has some shape like this. So there are apple and oranges. So I'm not talking about the color here, but let's say all we want the our computer is to I'll provide some apple pictures, I'll provide some orange pictures, okay, to the machine, and all I want the machine to identify, like it should identify whether it's apple or orange from the shape of it, okay. So generally how the data is created, so assume that this is the apple picture, okay, this is the orange picture, it's an orange picture. All when a picture is there, right, so let's say, let's assume this is solid, let's assume this is also solid, okay. So all it when we say like we provide a picture to the machine, we don't provide pictures to the machine. All we provide is data out of the picture, right? So the reason of drawing coordinates over here is I'll try to provide data in terms of coordinates. Assume that this is a whole layout. This is also a whole layout. And let's think of, do you know pixels? What is pixels? You heard of television, right? So full HD, SD ready, 1372 divided into 7868 or 1920 into 1080 pixel. So pixel is nothing but given a screen, what each unit of display. So like if you see here, over here, so what I'll do is like this is one pixel that is so to define an apple, I'm gonna say that okay, this pixel are kind of, assume this pixel are colored, or you can say that this pixel are let's imagine this is a black and white picture, okay. So we'll say that this pixel are black, and whether these pixels are, all these pixels are white, okay. So all we need to do is, over here this pixel size is not this big, okay, it is very small. So when I am drawing an apple, either a pixel will be totally black or totally white, okay. It will not happen that half of the pixel will be black or and half of the pixel will be white. It will never happen that. The pixel size is so small that when I'm going to draw an apple, the pixel will be either black or white, okay. So all when I'm passing this data to computer, like this apple picture to a computer, all I'm doing is I'm telling, okay, this is a layout, and I'm telling each pixel, like let's say this is 0,0 is a pixel, this is 1,0, this is 2,0, 3,0, right? Just imagine that this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. 1, 2, 3, 4, 5, 6. So you have like, I'm just trying to tell you like which pixel, what is the position of each of the pixel, right? So this pixel is nothing but the third pixel from the row, and let us say this is the 12th pixel from the column. So this is 3,12. This is the position of the pixel. All I need to say to the computer is whether it's a black or white. Whether it's a black or white. So I'm going to say, okay, this is a 15 cross 15 layout. This is a 15 cross 15 layouts, and all the black pixels, I'll only send what are all the black pixels, okay. I don't need to send which all pixels are white, because there is nothing drawn over here. I only need to set which all pixels are black, okay. Similarly for orange, I'm gonna send similar. So let's say this is 15 cross 15 and all the black pixels. Okay. And you will, when you will send, let's say this is one apple, one orange. There are similarly, let's say there are 100 images of apple, there are 100 images of orange. You will be sending data like this, right? And all the machine learning needs to define is based on which pixel size is black, which pixel size is orange. They have to learn whether it's apple or orange. Okay, so initially they will learn something. Okay, they may define some. Okay, this pixels are white and these pixels are black. It's an apple. Otherwise, it's an orange. Okay, in that first thing, 100 out of 100. Let's say apple is 100, orange is 100. In the first iterations, they says okay, 150 apple. They said 150 apple and 50 oranges. They made a mistake, right? They made a lot of mistakes, like 50% error is there, right? So then this is okay. This is the first iterations. Then they try to learn more. They then try to segregate the data a little more, and they come up with okay, 130 apple and 80 oranges. Okay, out of that, they'll still start making error, right? So like this process will iterate through, and they probably end with 102 apple and 98 orange. Out of this, actually 99 are apple, and out of this actually let's say 97 are oranges. Just giving an example. So this is almost close to 95% accurate, right? So probably you will come up with a model like this, where we can say that with a 95% accuracy, my model can predict whether it's apple or orange. Okay, so machine learning problems learns like this. So a machine learning method will learn something like this from the data. Okay, don't go by saying that hey, this is 95% is not correct or something. I'm just giving an example. Okay, probably this is not 95%, and probably out of 102, if 99 is actual apple, probably out of 90 oranges, probably 97 may not be the exact orange. I mean, by numbers, this may be wrong totally. What I'm saying is, but just an example. And all I try to give you is like another thing. What I give you is how generally images are being transformed into pixels. Okay, images has been transferred into pixel data, and that goes for machine learning. Did you understand that? How image recognition happening? Do you get an idea like how image recognition would have been happening, or how I can detect a human face versus a dog face?
Yes, Satya, very much clear.
Yeah. So this is what pixel do the magic. Okay. So when you are learning a machine, when you are into the machine learning model, so you wanted to, let's say, apply machine learning model on this particular. What is my drawing? Let's say you want to do a machine learning model to identify apple and orange. Okay, you have 100 apple picture, 100 orange picture. I can fit a model on all the 200 records, like 100 apple and 100 oranges, and fit a model with 95% accuracy, and I'll be ready, saying that okay, yeah, I'm ready now. Throw me some pictures. I tell you whether it's apple or orange. Is it a good way? Or what I'll do is I'm gonna take 80 apple pictures and 80 orange pictures randomly from each of the pool and learn a model. Okay, when I'm learning a model, actually the model knows whether it's apple or orange, and based on that it learns, right? That's how it is able to fit how much accuracy, how much error it made in the first iteration, then it try to improve. Next iteration, again calculate your error, then it improves continuously. If a machine learning model does not know the label of the training data, when I'm saying label of the training data means the label is it's apple or orange, right? Given a pixel record, it should know whether it's apple or orange. Then only it can fit and learn. So all I'm saying is let's take 80 apple pictures, 80 orange pictures, randomly selects 80 apple, 80 orange pictures, so that you don't somebody should not blame you that, hey, you have just taken the first 80 from each of the record set. What about last 20? What if the last 20 records of each of the sets are totally different? Totally, so let's say, like, what do we say? You have seen orange, right? There are two kinds of orange. There are some imported orange you see like every season you will see, and there are some Nagpur orange that comes, right? Just giving an example. So both looks totally different, right? What if all the 80 pictures in the beginning were of that Kunu orange? I think that's Kunu orange or something, and the last 20s were Nagpur Santras, right? Nagpur oranges. Those shapes are totally different. If you see Nagpur oranges, if I just give you a gray picture of it, it may looks like an apple. It may looks like an apple. Whereas the Kunu orange is totally round kind of shape. And in the apple, it can be a Fuji apple or it can be some kind of a Shimla apple or something. Giving it. So thing is, when you wanted to pick some selective records from a pool of large record, you should always do a random sampling. Like randomly you pick. Okay, what is random sampling? How you do it in R? You're gonna learn that in the future. But when I say random, like you just in arbitrary order, you pick 80 documents from Apple, 80 documents from Orange, and you learn your model, and you say that okay, 95% is my training accuracy. Okay, 95 is my training accuracy. Now, what about testing? You have still 20 Apple records and 20 Orange records are left, right? You ask this model to predict. So you basically took 80 and 80. You build a model, right? Let's say a model is M. Then you give this 20 apple and 20 oranges. Okay, so 20 apple and 20 oranges. Let's say this is apple, this is orange. Okay, and total is 20 and it is 20. Okay, and you ask this model, hey, can you, I'm just giving you some record without the label apple and orange. Now you tell me whether it's apple or orange. So what your model says is, model says apple. Let's say M means model is saying apple, and M orange is model is saying orange. Let's say model says orange is. So what happened is model says 21 of these 40 records, total 40 records you are asking to test. Out of them, 21, 3 plus 18. So 21 of them are it predicted to be orange, and 19 of the rest are predicted to be apple. Okay. Now, if you see here, if I add them up, this whole things become 19. And if you add them up, the whole things become 21. So 21 plus 19 is 40. And actually you have provided 40 records. But out of those 40, actually 20 were apple and 20 were oranges, right? 20 were apple and 20 were oranges. Let me know if you are not able to see this. Okay, it's now getting dirtier and dirtier. So out of 20, out of 19, so your model says 19 of them are apple. Out of the 19, the model says apple. Actually, 17 of them were correct, and 2 of them were wrong. Why? Those 2 were actually orange, and the model mispredicted it to be apple. So this is an error. In all the 21 fruits images that the model is saying it is orange, actually out of them 18 were correct. So this 18 is correct, this 17 is correct. Okay, this 18 were actually apple, actually orange, and the model also says orange. But this 3 orange prediction, the model, this 3 which the model says orange were actually apple. So now this 3 is an error. Now this 2 is an error. Okay, so all you do is, now how many errors I made? Like I made 2 plus 3, 5 errors out of 40, right? So maybe 5 by 40. How much is 5 by 40? 1 by 8, that is 12.5% error. So 87.5% is the accuracy if I just minus it from 100. So you can say that, okay, my now it makes more sense, because just fitting on the data, just taking everything as an input and saying that 95% is my training accuracy. That's not an accuracy. That's not a test, real test. You have not put your model into a real test where it has predicted something unknown for you, right? It is just trying to fit this 95% where it takes all the 100 records, that all the 200 records into account. It just fits a model. It says what is my fitting accuracy, what is my model accuracy. But here, when I did a 80 divided by 20 split, like 80 for training and 20 for testing, I'm actually putting this my model into test, right? I'm actually trying to give it a flavor in the future, like what you need to do in the future. Are you future ready? Is this model future ready to take some data and predict? Now, okay, I can say that, okay, this makes more sense, right? If I say, okay, from 80-80, if the model accuracy is 95%, but on a test, real test, my model is giving 87.5%, then you are more confident, right? You are confident that, okay, if new data sets comes in, which are unlabeled, I may be able to predict with a great accuracy, okay? That is why you should always divide. If when a data set is coming, you want to train a model, you should always divide the data into training and testing, okay? So 80-20 is generally a benchmark. Generally, we do 80-20 split. You can also do it 70% training, 30% testing. But there are different way of training and testing also that we're gonna talk about. There's something called cross validation. Okay, there is something called cross validation, which we'll talk in more detail in coming future. But the essence of talking all this is you need to divide data sets into training and testing, hide the testing data from the model during the training phase. Your system should only learn from the training data, and once the model is ready, it should predict. It should be tested on the testing data, and the accuracy should be measured. That's the real accuracy measure. If you just say what is your training accuracy, that's only the fitting accuracy, right? Because you knew everything and you try to fit. Obviously, you will get a higher accuracy. It's something like there is a like there are jyotis, right? So who can see your hand and they'll tell about future. They'll tell about past versus they'll tell about the future. Just assume that uh, so when somebody tells about your past, right? They are fairly accurate. You may be wondering that how can they tell me about my past or something. Assume that your hand lines and all that lines in your hand tells about your past very clearly because it has already happened. But predicting future is more difficult, right? Because that is something coming, right? And you have seen nothing. So just imagine training and testing is just try to see like training is being telling about past where you know everything and you are just trying to fit your knowledge and finding accuracy, whereas testing is about you are really predicting something which is unknown to you. Then you are measuring the accuracy, okay? Because when we are providing a testing data, we do not provide where the information whether it's apple or orange to the model, and the model has to say apple or orange. Then we open our book saying that, hey, you said apple, this is apple, but one of the record you say orange, this is an apple actually. One of the record you says apple, this is wrong, this is actually an orange, okay? uh, and model will not given a chance to saying that, hey, now you go and iterate again and tell me. No, model will just say whether it's apple or orange, and you just find out what is the accuracy of the model. That's all about testing. Okay, so this is my training, right? This is my training, this is my testing data set. So all I'm saying is, let's assume that being a circle or a cross actually depends upon the x-axis and y-axis value. Let's say I have only two inputs, x-axis and y-axis. What are the x-axis value and y-axis value, and what is the class will I'm saying will say that, okay, it's a cross or it's a circle, it's a cross or it's a circle, cross. And x-axis value, probably I'll say that, okay, if it is if x-axis values are like low, 1, and this is 4, let's say this is 5 and 5, 0, and let's say 0, let's say 1 and 5, this is 6 and 7, let's say this is 1 and 6, like this. So basically what I'm saying is, whenever x-axis value can be large, all you see here is x-axis value can be large, right? There is a range where x-axis values varies, but the y-axis values of this rate varies very less, right? Whereas for all this cross, the y-axis value range is pretty high, right? This is high, and x-axis value can be um, uh, anything, right? So all I'm saying is, let us try. All our input is x-axis value and y-axis value, all, and we need to predict whether it's a circle or it's a cross. So what I did is, I divided this data set into training data and testing data, and I need to predict circle and dot now. So let's say I defined a model. Okay, let me tell you what we generally call this model. We call this model as support vector machine. We'll talk about this in detail, but support vector machine is one of the best model in market right now, which can do classification. Okay, which can do classification. When I say classification, means predicting true or false, predicting circle or dot, predicting apple or orange. That's called classification. You will predict out of predict a categorical variable. Categorical means true, false, black, white, yes, no, right, rain, no rain. That is categorical. When what is numerical? Numerical means how much rain will happen. 20 centimeter rain, that's too much. Or 2 centimeter rain, or 1.5 centimeter rain. I'm telling about numbers. When I say numbers is my class variable, that is called numerical class variable. When I say whether it will rain or no, yes it will rain, no it will not rain. That's how I'm giving a definitive answer, right? A category, that is categorical variable. So when you are training a model which ultimate job is to classify a categorical variable, over here it's circle or dot, right? Sorry, not circle or cross. So this is circle or cross, circle or cross, right? So it's a categorical variable. All you wanted to do is classify categorical variable. So that's called classification. If I am trying to predict how much rain will happen tomorrow, or what would be my stock market value, how much my BAC index value will be tomorrow, that is called regression. Okay, that is called regression or forecasting. In regression forecasting, we predict numerical values. In classification, we predict categorical values. Are we clear on that? So SBM is a model which does classification. It will predict a class variable which is categorical. Okay, so let's say SBM here put a this is a linear SVM. This is a linear SVM. LSVM means linear SVM because it draws a straight line. This one you see, right? This is a non-linear SVM, non-linear SVM because it is a curve kind of line, right? So it's a non-linear line. So there are different SVM you can fit. Now let us say you fit a non-linear SVM and you say, okay, this non-linear SVM is 100% accurate because it was able to separate all circle from the crosses. Even a linear SVM is 100% accurate. But the real test will begin when you will test your model on the test data. Now, when you apply the non-linear SVM on the test data, you see that it is making lot of errors. So all I am saying is to the right of it, everything is circle. To the left of it, everything is cross. Now, if I say to the right of it, everything is circle, I'm making 1, 2, 3, 4, 5 mistakes over here to the right. To the left of it, everything is let's say if I say everything is cross, I make 4 errors, 4 versus 5. I make total 9 errors. But so I make 9 errors for the non-linear SPM, For the linear SPM, let's see how much error I make. To the right of it, everything is circle. So I make 3 errors. So 3. To the left of it, everything is cross. So I make 1 error here, right? So on this side, everything is cross, but one of them are actually circle. So I make 1 error. So 4 error I make, 9 error I make in nonlinear, 4 error I make in linear SVM. Just if you don't, if it's hard to grasp SVM right now, just think of a linear model and a non-linear model, because you are fitting a linear line and non-linear separation. Just think of this as separation line, okay? Now, which one is better? I'll go and choose this linear model, right? Because linear model is giving me more accuracy in the test data. As far as test data is concerned, I should choose linear model. So this is how you should be actually dividing the data into training and testing and do all this process before we publish a model. Yeah. And when you are doing training and testing, sometimes, not every time, sometimes you may need to introduce some bias. Let us say some bias in the sense you may need to simulate data a little and provide some extra records, or you may have to introduce little bias into. Let's say if you are able to visualize the data, you may be interested in introducing some bias, some training records which are maybe I'll introduce a circle here, which is in a lot of a circle here in a where all the crosses are there, or a cross here where there is a circle, just to introduce some bias so that to make the training data more robust. Okay, during the training phase, I'm just talking about the training phase. Or we may have to do something called cross validation. You have to iterate through training and testing. You can't just do one set of training and one set of testing. You have to iterate that process, like go on, choose different training size and train it, and rest you test it. Again, you iterate the same process, but this time you choose different training records and different test records, and then again you train your model and see how much it is doing. And you iterate this process, let's say 10 times, and see on average how much accuracy you are giving or how much error you are making. So something like that. So that is called cross validation. We'll learn that in detail, okay, going forward. And when you perform models, so now I'm gonna run through the slides because it doesn't make more sense. I'll just stop wherever it is required. Okay, these are all very theoretical general part, so not a much interest actually. So when I say how my performance of a model will be affected, okay, performance of a model will get affected due to various factors. First is what kind of learning algorithm you are using. That is also important. Okay, let's say if I know SVM is the ultimate model, and on along with that, if I use something called a naive-based classifier. Naive-based is one of the very basic model in classification. Okay, obviously SVM will outperform my naive-based, because by SVM itself is a very complex model and very up-to-date model, right? It's an advanced model. Obviously it will it will outlast my naive-based algorithm. So it depends on what learning algorithm you are using, right? More than learning algorithm, it depends on are we providing the right training data. So like are we training training our model on sufficient amount of data. That is also important. Okay, if in the testing phase, if there are millions of records gonna coming in future, and if you are training your model on 100 or 200 records, that's not sufficient, because 200 records cannot have all the properties of cannot have all the variations, right? Let's talk about simple language variations. Cannot have all the variations of record possible. So you have to train it on more data. right? And it also depends on, do you have any prior knowledge? Let's say you know something about the data sets, you know some properties about the data set, you should some way apply that knowledge before modeling. And if there is some background knowledge about the data set, that comes handy during the modeling. Okay. And the third point, if you see here, the type of feedback provided. Type of feedback is nothing but when you iterate through the process, you make first 40% error during the training, then you make 35, then you 30, 25, 20, and ultimately you make just 5% error, right? So in that, like, how am I iterating the model? What feedback I'm providing in each iteration so that I improve on and on. So this will become more evident when you learn neural networks and something like deep learning. Neural network is nothing but a deep learning model. Okay, this will become more clear to you. So it all depends on these factors. Okay, what algorithms you're using, how much training data set you are how much data set on which you are training on. Is the data set adequate enough? Does it represent the whole world, or does it have enough variations? Do you have any prior background knowledge on the data, or what kind of feedback mechanism you are applying when you are training the data? Apart from that, there is another factor called what is your modeling strategy. When you are saying that, what is your modeling strategy means, are you doing a cross validation? Are you dividing the data set into testing and training? All these are called modeling strategies. Okay. Another thing is optimizations. Okay, am I optimizing my model? So you will see that when we'll learn SVM or something like SVM model, you will see that there are some tuning parameters which you can tune to make model more robust or improve the accuracy of the model. Are we tuning that parameter, or you are just taking all the default assigned values? Okay, so it also depends upon, are you performing optimization or not. Don't worry about optimization. You will see, I can only show you a optimization picture when that particular model will come. Okay, so you will see that optimization criteria while we are learning support vector machine. Right now it is too difficult for me to also visualize what optimization is. Okay, this all you can learn, that's not a problem. Okay, we'll hold it here. What are different kind of machine learning algorithms? So by large, machine learning algorithms are of two categories. One is supervised machine learning algorithm, one is unsupervised machine learning algorithm. When I say supervised machine learning algorithm, that means depend algorithm. I mean, when supervised learning means, it is actually defining what kind of data set you are trying to adapt. So if there is a data set, if, for example, apple orange, I give you some pictures, and I know that which one is apple, which one is orange, and you need to create a model and tell me, given a picture, whether it is apple or orange. That is called supervised learning. Why supervised learning? Because there is a class, there is a label to each of the picture, that whether it's apple or orange. You know whether each picture is apple or orange. So when the class is known, we call it supervised data. The data is supervised. Hence, any learning onto that, any classification, prediction method applied onto that is also called supervised learning. Okay, like predicting whether it's an apple or orange is nothing but a classification, right? Because you are trying to predict a discrete level. Discrete is nothing but category. Okay. When regression, when it's a real value. So any classification, regression task, basically prediction tasks that we call prediction tasks, are supervised learning, because the training data has the answer to it. You know what is the answer of in the training data. You know whether it's apple or orange in the training data. If I wanted to forecast how much it will rain tomorrow, I'm going to take a history data for past 1 year. I know how much rain has happened in each day, right? So I know the outcome of the training data. That's why it is called supervised learning. For another example, I give you a set of pictures. So the pictures may be of apple or maybe of orange. The pictures may be a cow picture. The picture may be a human picture. A lot of pictures. Okay, I gave you all the pictures. All I wanted to say, ask you is, can you group similar pictures together? All I will say you is, please group similar pictures together. I don't know, even I don't know whether the picture is an apple picture, orange picture, cow picture, or a human picture. I don't know. I says, I have given you a set of pictures which are of different, some of them are of fruit, some of them are of cow, some of them are of human being. But I don't know what each picture is. I don't know the label. All I am saying you is, please group similar pictures. Okay, that means when I don't know what each picture label is, what each picture is, then it's unsupervised because I don't know about their class. Okay, or you can say class or label or tag, anything you can talk about, but the machine learning terminology is class. I don't know about the class value. I don't know what each picture is. That's nothing but class. Then it is unsupervised data. Okay, when I am talking you like, please group similar picture together, that is nothing but clustering. Clustering is nothing but grouping similar things together. So, and grouping similar things together, each group will be similar. Okay, I may end up with grouping all human being together, all apples together, all orange together, or all cow together. There might be some error. In the human being, I may have couple of cow pictures or couple of orange pictures, right? Because maybe orange in the sense, maybe the human head is round, orange is also round. Probably I may misgroup some of the orange to be human being, or some of the human being to be orange, whose picture there is just a head of a human being in the picture, not the full body. I may group them into orange. So that misgrouping may happen, but ultimately I may be able to. I'm just saying I may be, not very sure. Okay, I may be able to group all orange together, most of the orange together, most of the apple together, most of the human being together, most of the cows together. So that is like I'm grouping similar things together. That is nothing but clustering. Okay, we'll learn many more clustering algorithms, but as of now, clustering is grouping similar things together. Similarly, there are other techniques also, like find associations. I give you a let's say I give you bills of I provide you, let's say you are going to Hypercity Mall, Hypercity's retail store, and I give you details of all the items bought by all the peoples, all the items bought by each of the people who has visited, each of the customer. All you need to tell me is, okay, when somebody buys milk, they also buy bread. Somebody buys an umbrella, they also goes for a, most of the time they also goes for a what I can say, slipper, rubber slipper. Okay, probably because it's a rainy season, somebody is buying umbrella, they may also like to change their shoes to a slipper because because of the rain. Somebody buys a let us say somebody buys books, somebody buys a notebook, not laptop, this simple notebook. He may also buys a pen or pencil. Okay, so similar things. So in that case, when I'm providing you records like items bought by each of the customer, I'm not defining, right? There is no class to it. I'm not saying this customer, I'm not saying anything about other than what items they have bought. So when that kind of like transaction records, when I'm providing you transaction records, they are unclassified. They are not classified documents. So they are unsupervised data. So finding this kind of problem like milk along with bread, or pencil along with notebook, or a slipper along with a umbrella, these are called association. Okay, we call this association rule mining or frequent set mining. This also is not a part of our curriculum, but I'm going to teach that also. So association frequent set mining, right? Or if you have heard of cross selling, or recommendation engine. Have you heard of recommendation engine? That is nothing but association rule mining or finding association. Okay, that is this is also unsupervised learning, because the data that on which it is learning is not a classified data. It's not a classified data. That's why it is unsupervised learning. Similarly, there are techniques called dimension reduction, because whenever there is unsupervised learning, you want to do clustering, or you want to do let's say for most of the time for clustering, there might be 100 columns, like there might be 100 features. Okay, there might be 100 features. Imagine I ask you to visualize it to uh, um, a two-dimension graph. You can easily visualize. Imagine I ask you to visualize a three-dimension graph. That is also possible, right? Three-dimension graph, you can draw it in the paper. Imagine I ask you to draw a four-dimension graph. Can you draw a four-dimension graph on a paper and try to visualize somehow? No, it's not possible. Imagine I ask you to draw a 10-dimension graph. That's even not out of question, right? So what if there is a technique I can bring down a four-dimension graph? When I say four-dimension graph, means I have four axes, right? X, Y, Z, T. Let's say X, Y, Z, T. Four axes. What if I have a technique? I can bring down a four-dimension graph to a two-dimension with all the data intact. Every data will be there, but I'll reduce the dimension. Then I can easily draw a two-dimension graph, right? So I'll say that, okay, this is a two-dimension representation of a four-dimension data, or this is a two-dimensional, three-dimension representation of a 10-dimension data. So all you need to do is bring down the dimension into less number of dimensions, right? So that is we call dimension reduction technique. It is very useful in terms of clustering when you group similar things together, because it reduces the dimension. When the dimensions are reduced, your clustering, your modeling approach will be super fast. Okay, it will, the modeling training time or the clustering time will be very less. Okay, that's why dimension reduction is useful. Similarly, semi-supervised learning is a mixture of this. I'm going to talk about this little more later, because this is a very initial stage. It will be difficult for you to understand what is semi-supervised learning. We'll talk about this later. So imagine that you are having, it is just about like you have some labeled data and there are some unlabeled data, like some unsupervised data. You mix them together and do a classification on top of it. That is called semi-supervised. Like some supervised data, some unsupervised data, and mix them and try to learn. That is called semi-supervised. And reinforcement learning is nothing but it's a kind of dynamic programming. If you remember, if you all are from computer science background, or if you have there is a course called algorithm in your studies, there is something called dynamic programming, if you remember. When this reinforcement learning are nothing but a dynamic programming, when it dynamically try to learn from the data. And just hold on your thoughts for a little. For semi-supervised and reinforcement learning, we'll talk about this later. Okay, when we have time, we'll go through this. Okay. So right now, I'll not talk more than this, but if you want to do a search, please go ahead and search. If you have any doubt, you can ask me those questions, but I'll take it easy. I'll explain this later. Okay. When we have a little more time, I'll explain this later. Yeah. So if you see here, when I say supervised learning, I know what each of those data set class is. I know this is all circle. I know this is all cross. I know this is all star. When it is unsupervised data, I don't know class of each of them. Everything looks similar to me. Only the properties are different. But like properties means if this is x-axis, this is y-axis value, only they are different. But I don't know whether it's a circle or a cross or a star. Okay. When it's a semi-supervised, this is a little mix. Like I know some of the records label, but I may not know some of the rest of the records label. So the unknown labels are this one diamond shape that you see, right? Diamond shapes are spread across all those three classes. But for some of the records, I know the classes. If this is the kind of the situation, then it's all learning that you do, all machine learning models that you apply on this kind of data are called semi-supervised. Okay. And this is a supervised learning technique. How it does is like this is a training data. A training data can be anything. It can be a simple a table, a perfect table. When I say table, means a SQL table where you have all the data set perfectly labeled, or it can be a image, it can be text, anything. And when I'm saying it's a supervised learning, that means each of this particular record or each of the document or each of the image will have a label associated to it. Okay. And you're gonna find feature vector. Feature vector is nothing but properties. If I'm saying x-axis value, y-axis value, or if I say, okay, I want to predict, I want to predict how much how much electricity consumption will happen at a particular city. For that, I need to know how much rain will happen, how much, what is the visibility, whether it's a working day or not working day, whether it's a rainy season, whether it's a summer season or not a summer season, right? Whether all those things, right? How much electricity consumption happened yesterday. Those are called feature vectors. Okay, those are called feature vectors. And label is how much electricity consumption happened today. I mean, in a record, in the past data. So take all this, build a machine learning model, and which is able to predict, then this is a new record. Now, new record will come for which you do not know the label. You do not know the label. And the model will basically predict the expected level of this record. Expected level of this record. When you are building a machine learning model, you have to take care of everything. You have to divide this data set into training and testing, do all those workflow, train, then test, verify the model is good or not, then publish. This is a published model. After you do all your effort, this is a published model ready to predict any coming near future data for which you need to know the level of it. And it can give you expected level of this data. This is a general architecture of supervised learning. Okay. Similarly, unsupervised learning, all the difference that you see here is unsupervised learning does not have a level. Okay. All you may need to do is you may need to group similar documents together, group similar records together. Okay. It's more, I mean, one of the major usefulness of using unsupervised data or unsupervised learning is to cluster. Okay. Beyond that, there are some more techniques like association rule mining, the recommendation engine, and clustering. These are the two major algorithms in the space of unsupervised learning. Okay. So it's all about grouping things together, finding patterns out of it, like milk goes with bread or notebook goes with pencil. Okay, that's pattern. It's called pattern. You have to train a model, either a clustering or association rule mining model, and that model, when a new record comes, some new buyer will come, will buy some bread. You're gonna suggest, sir, there is an offer in the milk. If you buy milk today, I'm gonna give you one rupee discount. Okay, or if you are buying a pencil with a notebook, there is 5% discount on the pencil price. Okay, just giving an example. Who gives 5% discount on pencil? But this is just an example. Okay, that's all about how you be using association rule mining. Similarly, clustering you will also can useful. I'll not talk more about this because we're running out of time. Okay. Now this one, okay, this is all about underfitting and overfitting. Okay, what happens is generally, I'll not talk more about this graph, but I'll just tell you one small thing is when you are trying to when you are given a training data, and all you divide is when you given a history data and you divided the data into training set and testing set, and you fitted a model. You fitted a model M1, which gives you, one second, let me go to this. Fitted a model M1, which training accuracy is 99% and testing accuracy is 70%. Okay, I fitted a model M2 whose training accuracy is 87% and testing accuracy is 83%. Oh, okay, 83%. You know, actually this model is good. I'm not going to ask you which model is good right now. This model is good because the training and testing both are fairly okay and both are nearly equal. So whatever the training accuracy you are getting, when you tested also you got similar kind of accuracy, and you are more confident in saying that I may get more than 80% accurate. My model is more than 80% accurate. But here you are confused because your training phase is 99% accuracy, but when you tested it on the little data that you have kept hidden, it just gave you 70% accuracy. So the testing accuracy went down by a large amount, right? Why? Because you trained a model which overfitted the training data, That is not good. Okay, that is not good because overfitting is like getting biased towards what you are seeing, getting too much biased towards what you're seeing. Like example of somebody is just believing what a saint is saying and is not believing on the science at all. Is like getting biased towards what somebody is saying. So it's like the model is getting biased towards training. So it is overfitting the data. That's why 99% accuracy is coming, and in test it is just 70% accurate. If it is a true fit, you should ideally see similar kind of accuracy in the tested as well. So this is a clear cut case of overfitting. Similarly, underfitting also. It should not happen that training model should give 30% accuracy or something. I mean, that's clear case of underfitting. You can't underfit data so much. I mean, you can't train a model which just gives you below par, like less than 50% accurate. That's even bad, right? So underfit is anyway out of question, but overfitting, you should be cautious about overfitting. You should not fit a model where the training accuracy is too high and the testing accuracy is way lower than training accuracy. That's a bad modeling. Whereas this is a better modeling. Although the training accuracy is not that high as this, but the testing accuracy is very similar to the training accuracy. That's a better model. So this model will be selected over this model. This model is okay. This model is no. Okay, because of overfitting. Okay. Similarly, when we are doing a supervised learning, there are various ways of supervised learning. One is you will do a regression based, or you will predict numerical values. So that is called linear classifiers. Okay, you just do a numerical functions, or you just predict numbers. When you are doing a classification are defined in two ways. One is parametric, one is non-parametric. Okay, let me tell you about parametric. Chances of raining tomorrow is 80%. If I say, that means chances of not raining is 20%. That's a parametric model output. Whereas non-parametric model it will rain. I'm going to say that it will rain. No probability. It will rain or it will not rain. Okay. When an output of a classification model is just cut to cut, it will rain or not rain. Okay. Yes or no. That is called non-parametric. When the output of a model is what is the probability that it will rain? 98% probability that it will rain. If the model gives a probability value of an outcome, that's called parametric. Okay. If it does not give you probability, it will just tell you which category it is. It will rain or not rain, then it is non-parametric. Okay. We'll not go detail into each of the model. Anyway, we are covering a lot of models going forward. Okay. Similarly, non-metric is in the sense like it will tell you, okay, whether it will rain or not rain, but based on certain condition it will tell you. If wind is blowing, if the temperature is less than 25 degrees Celsius, it will rain, something like that. Okay, so that is like rule-based outputs are generally called. Then it will rain. Then that is called non-metric. Okay, don't worry, we are going to talk about each and everything in detail going forward. Aggregate is, let's say you have 10 models. If you have 10 models, 8 of the models is saying it will rain, 2 of the model is saying it will not rain. So what do? You are confused, right? 8 models are saying rain, 2 models output are saying non-rain. So I'll go with 8 models because majority of the models are saying it will rain. Only minor models are saying it will not rain. I'll go with saying that it will rain. So that means I am aggregating. I'm aggregating the output of 10 models, or I'm going by a majority vote, right? So those are like aggregations. Those are called aggregation, or we call, it's a better name is ensemble learning. Don't worry, this term is not written here, but it is there in your coming classes. Ensemble learning. Okay, that means aggregating multiple models output. Okay, so that is another way of supervised learning. This is an advanced way of supervised learning. Don't depend upon just one model. Train multiple models and aggregate their results. That's all about aggregation. Okay, we are not going to touch all this. Anyway, these are all will be covered. Okay. Perceptron, this is all training testing. I have talked a lot about this. I'm not going to touch base on each and every algorithm in detail because they are already there. Perceptron learning algorithm is nothing but a neural network model, whereas logistic regression is another classification model. It's a classification model. This is nothing but SVM, support vector machine, that I am talking about. All it is trying to tell you is, see, you can't fit a linear model, linear SVM here, because linear SVM will not work. All you need to do is you need to find a model which can draw a circle here, because if I can draw a circle here, all the points inside the circle are red circles. All the point outside these dotted circles are nothing but cross. So all I need to know is I need to build a SVM which can draw a circle boundary, not a linear boundary. Okay, so that's why it's a linear to non-linear transformation that we need to know. That is done by making the data into higher dimension. Instead of 2 dimension, I have to create more dimensions. Okay, we'll talk about that later. This is too much to digest right now. Just giving a glimpse of what we're going to learn in coming future. Okay, some more, as I already discussed, these are like few of the unsupervised learning techniques. Clusterings, you're going to learn about all this k-means clustering, density-based clustering, spectral clustering. All this are there in the future. And there are some density models will be there. Dimension reduction, I already told you, right? How do I reduce 4-dimension space to 2-dimension? That's all about principal component analysis and factor analysis. Those are all some techniques to do that. Some techniques to reduce 4-dimension data to 2-dimension data. Okay. Okay. Now, where all this application will happen, as I all told you, face detection, right? Like where I can tell you, okay, face of all three of you give me your different photos. I can actually do a machine learning model on it, and given a photo, I can tell you who one is this. Whether it is, sorry, I still not remember your name. Whether it is Ayush or Sadanand or it is Sudhanshu, that can be told. Okay, using machine learning model. So that's nothing but face detection. Object detection, I already told you, whether it's apple, orange, or it's a cow, or it's a human. That is image segmentation is grouping different images together. There are many applications like rain forecasting, anything that you know, right, where you feel like analytics is used, machine learning models can be used. So I'm not going to talk you through about what all things we can do. Okay. Machine learning are applicable in many spaces, right? Speech recognition, NLP, natural language processing, like understanding a computer understanding texts is very important. Okay, is one of the advanced uses of these days. Like everybody is into NLP, natural language processing. Like computer should understand a text the way human understands. That is all about natural language processing. Medical outcomes like medical diagnosis, finding similar X-ray reports or finding similar biopsy reports or finding similar MRI reports. All these are like can be you can use machine learning on it. Okay, there are many ways. I mean, there are not even a single area where research is being done and they want to automate the process and machine learning is not used. Everywhere machine learning is handy. Okay, probably some of them are very advanced, some of them are learning, trying to adapt machine learning, are very new, but it is coming handy in a lot of areas. Now, why it is accelerating? Because anyway, there are more and more advanced machine learning algorithms are coming. There are sensors are everywhere, right? You have sensors, like even a car has a lot of sensors, so you can actually diagnose a car using machine learning algorithm. For at what time it should go for a service, it can also be learned from the past data, from the past sensor data, and when you went for a servicing of your car. If I get all those data, I can tell you for next you should go for a servicing. That is also possible. Okay, so there are many. Data is growing. Actually, data is growing. So that's why if there is data, there is always machine learning model will be coming handy. If there is no data, I can't apply machine learning model, right? Similarly, there are different easy way to write algorithms, right? R is there. You can easily write a machine learning algorithm. Python is there. A lot of libraries are also there. So, like contribution to machine learning world is also a lot. So that is why adaptation of machine learning algorithm is so easy these days. Okay, I'm not going each by each term. Okay, here you can just read it out. This is nothing, just some plain English. This is already we talked about. You can go through them. This is what I was trying to say. Like if I learn images of all, if you see the 4 images of, let's say, this is how Ayush looks like. So if I get 4 images of Ayush, I can learn, and given it some test image, I can say this one is Ayush. I can say that. Okay, that is called face recognition. Similarly, let's talk about this. I can the way you navigate car, it will say I install a camera onto your car and take all the images, all the video images, and see how you are, exactly you are steering, you are twisting, doing the angle of your steering, what distance you are controlling your steering, how much angle you are rotating your steering. If I get all this information, I can also learn that same thing by looking at your all past data. I can tell you how much rotation you need to make your steering to take that turn. That is also possible. So this is a regression based application. Okay, if I get all this data, this can be done. Okay, just go through all this. I'm not okay. As I already told, right? Supervised is all about the class variable. Anywhere the data in the past data there is a label to the data is supervised learning. Anything that is unclassified, anything that we applied on unclassified data are unsupervised. Next class tomorrow we are going to learn is K nearest neighbor. This is it. A K nearest neighbor is nothing but a classification technique. Okay, K nearest neighbor. This is one of the very easy model that we're going to talk about, but there are a lot of complex things also about it. We'll try to simplify things and learn tomorrow.